This is differential equations day number 7. Topic is the integrating factor method. So each of these items here that I'm going to star here are items that we established in the derivation of the integrating factor, which you can find in my separate video within the same folder that you found this one. So I'm not going to go into that on this slide. I'm going to get into some practical use of the integrating factor. So let's go ahead and get into a few examples. Okay, it says in example A, find the particular solution to the differential equation given the following information. Okay, so first off, I do want to identify that I need to put this differential equation into the form dy dx plus p of x y is equal to q of x. All right, so I'm going to identify a few items here after putting this differential equation in that form. So I would have dy dx plus y is equal to e to the negative x. All right, so what that does for me is I can now identify p of x. So p of x is going to be 1. Okay, you can see that it's the function multiplied by y is the function, constant function 1. Q of x is going to be e to the negative x. Okay, now we're going to have to do a little work here, of course, to identify I of x. I of x, as we know, another item that was given based on our derivation is e to the integral of p of x dx. All right, so let's integrate p of x. So I of x, which I'll put in green here, will equal e to the integral of p of x dx, which is 1 dx. Okay, therefore I of x will equal e to the x. Now, I don't need to put a plus c there, and that I can go into in a different video if you'd like me to, but that's going to be my value for I of x. Now, the third item that we talked relatively in depth about is that the chain rule, the product rule is what built the possibility of this thing called the integrated factor. Okay, so the derivative with respect to x of y times I of x, and this, for whatever reason, I can't write it right next to it, is going to be equal to I of x times q of x. Okay, I multiplied by the integrated factor throughout the entire expression, and I get that. Okay, again, questions with why that is, you can talk to me on the side. Okay, so the derivative with respect to x of y times I of x, of course I've identified I of x, right? I of x is e to the x. Okay, would be y times e to the x, and that'll be equal to I of x times q of x. So that's e to the x times q of x, which is e to the negative x. All right, now, where did p of x go? P of x was only useful in finding I of x. All right, so its use was depleted in finding I of x, and now it's no longer to be used. All right, so let's simplify a little bit here. So the derivative with respect to x of y times e to the x, or y times I of x, is equal to e to the x times e to the negative x. And what that ends up being is just 1. Okay, now what can we do with this? This is now in a form where I can integrate both sides. So if I took the integral of a derivative, if I took the integral of the derivative of y times e of x, I would just get y times e of x, or e to the x. On the right side, the integral of x is going to, or of 1 with respect to x, will be x plus c. All right, now is when I employ my initial condition. And of course, that initial condition is the point 0, 1. So y is 1 when x is 0. Therefore, I would have 1 times e to the 0, which will be 1. And I have 0 plus c, which will be c. So c equals 1. Thus, y times e to the x is equal to x plus 1. Now, to solve for y, what I would do is divide both sides by e to the x. which would be x plus 1 over e to the x. Or if IB, for some reason, whatever reason, required it in a certain form, could be written as y equals x e to the negative x plus e to the negative x. And there you have it. That is your particular solution to the differential equation using the integrated factor method. Let's try another one. Okay, looking at example B, you can see that this is not quite in our form that we want, right? We want dy dx plus p of x times y is equal to q of x. Okay, so what I need to do is notice that this dy dx is multiplied by x. I got to divide all terms by x. So that gives me dy dx is equal to 5 over, oops, I'm sorry, not equal to, plus 5 over x times y is equal to 6x squared. I divided that term by x. Okay, so let's identify p of x, q of x. So p of x is going to equal 5 over x. Q of x is going to equal 6x squared. All right, so I of x will equal e to the integral of, I'm going to put 5 times the integral of 1 over x dx. I do that just to keep things simple, which means that I of x will equal e to the 5 ln of x. Okay, we got to use some properties of logarithms here. I can get some this into a much simpler form if I use the property that this would be e to the ln of x to the 5th. Now that will reduce, right, using properties of logarithms and exponents again to x to the 5th. Therefore, I of x is x to the 5th. Okay, so knowing that, and knowing that the derivative with respect to x of y times I of x is equal to I of x times q of x, what we can say is that the derivative with respect to x of y times x to the 5th will be equal to I of x, which is, like we said, x to the 5th times 6x squared. Okay, now we did a lot of work on the right side so that we can do just a little bit of work in finding what our function y is with respect to x. So I'm going to integrate both sides with respect to x. Of course, when you integrate the derivative, you get y times x to the 5th is equal to. And now this term here is actually the integral of 6x to the 7th with respect to x. Let me put that in the colors that we used earlier. Okay, so the integral of 6x to the 7th, what would that be? Well, y times x to the 5th would equal x to the 8th, 6x to the 8th over 8, or 3x to the 8th over 4, plus c, of course. Okay, walk yourself through that integration process on the side if you need it. If you got questions, let me know. So now I'm going to employ my condition given above, the initial value, 1, 4. So I'm going to plug a 4 in for y and a 1 in for x. Therefore, I would get 4 is equal to 3/4 plus c. So we will get 13/4 is equal to c. Now let's do a little work to find the particular solution. This would be y times x to the 5th is equal to 3x to the 8th over 4 plus 13/4. All right, I'm going to divide everything by x to the 5th. All right, and see how I rewrite this. To get y all alone, I would have 3x to the 3rd over 4 plus 13x to the negative fifth over 4. Now that can be rewritten in a number of different ways, but those would all be equivalent. And depending on what IB requires for form, you might have to adjust that. So there you have it. There's the particular solution to that initial value problem. Let's look at one more example. All right, here is a here's a nice example. I really like it. I want to put this again in my form, dy dx plus p of xy is equal to q of x. Okay, so I'm going to need to divide everything by tangent. Now, let's talk this through. If I divide everything by tangent, I would get y over tangent, or cotangent of x times y. And if I divide sine x over tangent, let's do that. Sine x divided by tan x is the same as sine x over cosine x. Okay, which is equivalent to sine x times the reciprocal of tangent, which is cotangent, which is cosine x over sine x. So you can see the sine x's reduce. So sine x over tangent x is cosine x. All right, so p of x is equal to cotangent of x. Q of x is cosine x. Okay, let's find I of x. I of x is equal to e to the integral of the cotangent of x dx. Now let's work the integral of cotangent down here. I'm going to write cotangent as cosine x over sine x. So this is the integral of cotangent of x. All right, that's going to involve a u substitution. Now if I called u sine x, conveniently du is cosine x dx. So that'll be a nice little substitution. I'm going to do the integral of 1 over u du, which is the natural log of u plus c. Now again, with the exponent in I of x, we don't have to worry about plus c. And that again can be a side note if you want to talk about it. So this would be the natural log of u, which is sine x. Okay, so I of x is equal to e to the natural log of sine x. And of course that will reduce to being just sine x. Okay, so we've got I of x. So recall that the derivative with respect to x of y times I of x will equal I of x times q of x. All right, so let's rewrite with what we know. So I of x is sine x, q of x is cosine x. All right, so I've got y times sine x equal to sine x times cosine x. What color? Oh yeah, blue. Dx. Now, I've got a way to make this much simpler, and I'll show you what that is in just a moment here. Okay, so the integral of the derivative of y times sine x is just going to be y times sine x. And, I mean, we could do a substitution of sorts here, which would work just fine. I'm actually going to call this the integral of, oh boy, what do I want to call that? Let's say, okay, I got an idea. So sine of 2x is equal to 2 sine x cosine x. So sine x cosine x is 1/2, excuse me, sine 2x. Okay, so I'm going to integrate here 1/2 sine 2x. All right, so y times sine x is equal to 1/2. Now the integral of sine x is negative cosine x. Okay. Negative cosine 2x. But I must account using the chain rule for that 2 inside. Okay, so if you took the derivative of that, you should get sine 2x, right? Or, excuse me, 1/2 sine 2x. Okay, of course, and then plus c. So let's clean that up just a little bit. That'll be y times sine x is equal to negative 1/4 cosine 2x plus c. Okay, so let's do this. Let's use our initial condition, which is pi 0. Pi for x yields a 0 for y. So on the left side, of course, I plug in a 0 for y. That'd be 0. Just so you know, sine of pi would also be 0. So I get a 0 on the left side. On the right side, I'd have negative 1/4 times cosine of 2 pi. Well, cosine of 2 pi is 1. So I would have negative 1/4 plus c. All right, so I know that c then equals 1/4. So I can now write y sine x is equal to negative 1/4 cosine 2x plus 1/4. All right, let me scoot this screen down just a tad and go from here. Okay, so if I divide everything by sine x, I would get, let's do this. Let's go negative 1/4. I was going to try to do something fancy, but I'm not going to do that. Cosine of 2x over sine x plus 1/4. And instead of putting this as 1 over sine x, I'm just going to write it as cosecant x. Now that can come in many forms, guys, many forms. That's just one of them. Okay, so beware of if IB gives you a form that they want it in. Otherwise, that's it. The integrated factor, it's good stuff. See you in the next video.